Okay, so the tutorial from last week is already there. You can take a look at the notes. I think I might still do the deletion rotation maybe together with all of you just once. I think it's definitely complicated enough. I think it would be better if I can do it together with you. But anyway, it's going to be the starting point for this Thursday. We'll do some paper exercise. And then we might talk a little bit about assignment number 1. We'll do some relevant exercises. Your assignment number 1 will be released tomorrow. I'm hoping maybe by the early afternoon, the earliest, or maybe early evening, but for sure tomorrow. I'm just finalizing some details about the assignment. But it's going to be fun exercise for you to do, especially you get to do some rotations from scratch. Okay? But you get, we'll talk about it maybe in the tutorial, not in the lecture. Okay? And then we got 2 more weeks before the reading week, so you definitely want to make sure you work on the assignment 1, especially the programming part as much as you can, and I will try to give you some idea or tips about programming test 1, which will happen after the reading week. Okay, so that's something definitely keep in mind. We are following the calendar strictly. Okay. Any questions about the course so far? All right, good. Okay, let's do a very quick recap about last time. And then we shall do some fun exercises today and also continue with the definition for the graphs. Okay. So last time we introduced the idea about graph, right? It's really a big topic. We're definitely going to spend a lot of time until the semester ends, for sure, right? So we talk about definition. So whenever you want to more like a formulating what a graph is, it's going to be a tuple. And then you got a set of vertices, also you got a set of edges. Each edge will be sometimes it may have a name. For example, you might see sometimes we put an n over here as a name for the edge. But sometimes you might put some weights, like an integer here. But the weight is something we'll talk about later. But I'm just saying, you got to be more, there might be different variants, for representing the graph. But for edges, definitely will always work just by a pair of vertices. For example, edge over here will be A and B. All right? Depending on whether there's a direction there, so you may also have to worry about maybe only A to B is defined, but B back to A is not defined. Right? You want to pay attention to such details. And we talk about the vertices and edges. They are relevant or illegitimate universes of this closure. So for many of the properties and definition we're going to see in this course, we're actually going to use universal, existential, sometimes even nested to actually express the idea. We'll see many examples, maybe even today. Okay. So you guys really want to get back to, about the math mode, about how to use a practical logic, and also how to formulate properties and proofs as well. Okay. Okay, and we spoke about directions, right? So yeah, so you guys can review the detail. Just remember, why do you need a directed graph as opposed to undirected graph? It's really about dependency, flow, and also order. Okay, we'll see more and more examples as we go. Okay, directions. And self-loop and multiple edges. So these are the 2 things we don't really see a lot in this course. But I think this one is quite common, self-loop. For those of you who may want to work on, for example, software testing, so whenever you want to draw a state diagram for your system to derive test cases, self-loop is actually quite common, right? But just for many of the properties that we talk about, we simply assume for simplicity, it's simply a simple graph, which means we have no self-loop and also parallel edges, right? Just notice about the assumption that we are making. And degrees, right? We'll do a nice proof about degrees from different vertices today, right? That's something I want to do after recap. So the degrees will simply be the number of edges connected to a particular vertex, right? So that's the very definition. But if you got a directed graph, you got also the so-called out degree, which will be the number of outgoing edges from a particular vertex. In this case, the out degree for A will just be 2. On the other hand, there is another incoming edge going into A. So that's so-called in degree, right? Out degree, in degree. If you add them up together, it will be the whole degree for the vertex. All right, and then, so this is a property that we spoke about last time. So think about every time we introduce a property, right? Number 1, know the definition. Know exactly what the property is trying to say. Number 2, you want to be able to apply the property into some example graph. Of course, example graph may not be given to you always. You want to be able to draw some graph yourself. Maybe sometimes I will even say, consider the following property for graph. You want to determine whether or not it's actually legitimate property. If you want to show that it's legitimate property, you want to prove it by mathematical induction, which we'll do today. I Let me just write it down. Actually, I think it's quite a nice thing for you to remember. Okay. And we got other definition you can refer to. I think this will be the last part. I think we might just recap. Okay. So whenever you're given a property on the graph, so let's say you're given certain property on graph. Okay. Of course, the graph over there, we may qualify the graph by saying, oh, maybe it should be simple or not simple, directed or undirected, etc. Right? You want to pay attention to those details. And I would say even before you think about whether that property is really true or false, just try some example. Okay. So I would say application. Okay. Basically, you just want to apply the property to some example graph, just to get some intuition. And then the question might be, prove or disprove this particular property, right? If you want to prove it or not to disprove it, right? And then the next question will be to prove or disapprove. Let's link a little bit to our math lecture, right? If you want to prove it, you're basically saying this property here is going to hold on all the possible graphs that we assume, all right? If you want to prove it, you basically say for every graph that satisfies the kind of assumption we're making, for example, a simple graph, or maybe a graph without any cycle. That's something you usually can search from the property definition itself. So for every graph, this particular property P actually holds. So that's really what you want to prove. All right? So the way to prove it, which we'll see in detail today as a first example, is by using mathematical induction. Okay? So the way to do it is by using mathematical induction. Which in some way is a very close to how you define for recursion. So up to this point, you guys have seen many recursions, maybe from 2030, 2101, or maybe in your math course. So mathematical induction is definitely something you have to worry about for this course. Okay, we're going to do lots of examples as we go. Okay, and how to disprove it, right? So now, if you want to disprove it, you basically want to show that this for all is false. How do I show that for all is false? You basically have to give a witness to say that for that particular witness graph, it's not going to hold for this property. Right? Just need to give one. But of course, whether or not you can come up with a witness, that's the issue. Right? So you're going to have there exist some graph G. Not the case, the property holds on that particular graph. So basically using a witness, choose a witness to show that the property does not hold. All right, just keep this kind of in mind. You can think about it as more like a strategy, right? So if I simply say prove or disapprove, you have to first of all make a decision whether you want to go for the green one to prove it or the red one to disprove it, right? Once you make that decision, go for that. Okay. Yes?
Do you want a counterexample?
Yes, exactly. That's another way to call that, yeah. Witness or counterexample, yeah. I will write it down. Witness, as your fellow student correctly also pointed out, is also counterexample. An example to prove some violation. Okay. Okay, so that's something to, for us to keep in mind. Okay, and then you guys can just go over last time's lecture, right? So I think that's enough for recap. Okay. All right, so today I want to, very quickly, so there's something I kind of forgot to mention, but it's on your slides, okay? So we spoke about this property over here, right? Given that the graph is simple and undirected, this property here will always hold But I can tell you for this one here, you cannot disprove it. You just got to prove it, right, using mathematical induction. I'm going to do on a different example, but this one here will be for your exercise to prove by induction. Okay? So here we're talking about the upper bounds for the number of edges, really, right? So I just want to mention that there's a very important definition. Okay? So when equal is actually the case. So that means your number of edges is exactly equal to n times n minus 1 divided by 2. Meaning that for every vertex we have in the graph, you got connections to all other graphs except for itself. Right? That's why it's n minus 1. Right? That's something we kind of briefly spoke about at the end last time. Okay? And if you have this equality holding, that means the maximum possible edges, you call this graph complete. All right, so if this is the case, that means the graph you have is complete. On the other hand, if it is the smaller than sign, that holding, you just say not complete. Okay, just notice that distinction about definition. That's on the slides anyway, but I just want to mention that. Okay. Okay, so that's about that one there. And then let's now talk about this property here. So last time, we tried to apply this property here on some example graph, right? That's what we did. But now we want to prove it, right? So now you're given the question. We know that this is a property that's going to hold on any graph that's both simple and undirected. And now we want to actually prove it, right? And notice that the property itself doesn't really say non-empty graph, which means you may have to consider empty case as well, right? If anything that's not explicitly assumed, you cannot assume it. You have to consider in your proof somehow. So we're just going to prove by mathematical induction. Okay. So let me, okay, I think maybe I'll make that one tutorial session either, could be this Thursday, I'll see. Either this Thursday or maybe next Thursday before the reading week, we can do more exercises on the mathematical induction, right? I'll prepare some example, we can do it together, okay? But the pattern is gonna be very similar, okay? So basically, when you do mathematical induction, very quick, about a step you can expect to see. Mathematical induction. Okay? And what I want you to compare as I try to write out the critical steps, it's very similar to how you program recursion. And not surprisingly, one of the exercises we're going to go over in this course is to see how you can prove correctness about recursive method. How would you prove it? Mathematical induction, because they correspond to each other very nicely. Okay? But there's something later. Okay? So, step number one would be we have the proof about base cases. So you have some property P, and you just have to choose some base cases. For example, we might want to say we want to prove mathematical induction on the number of vertices. Number of vertices can be 0, can be 1, can be 2, and etc. 2 was very large. Okay? So you can maybe choose maybe 0 and also 1. And typically 1 or 2 should be enough. Okay? Just to make sure the base cases will actually hold. And for example, you can think about the 0 over here really can be maybe an empty graph or it can be empty tree. And I'll definitely do one mathematical induction example with you about trees. That's also very interesting. Okay? That's the example I usually did in 2101, but I think it's still very relevant to what we are doing here, just for review. Okay? Okay, so base cases will be step number 1 and step number 2. You basically, you have to state the so-called inductive hypothesis. Inductive hypothesis. Sometimes just say IH. So basically we want to say, we assume the property will actually hold on certain input size. Okay? We basically say, assume the property that we want to prove will actually hold on certain size of the input k. And the k here is larger than base cases. For example, k will be larger than 1, since we already cover 0 and 1. So we just cover 2 and onwards, basically. All right. Inductive hypothesis, I would say that's really the most important bit for your proof to work. I would say for many of the properties, inductive hypothesis may be more like a summary or more like an extract from what you read from the property. That could be one extreme, but there will be some cases where you have to somehow formulate the inductive hypothesis yourself. You will see some example when we prove about Dijkstra algorithm. That's something we'll see. Okay, later. That will be for assignment number 2 or 3. I forgot. Right, one of the later assignments. Okay, number 2 will be inductive hypothesis. Number 3 will be something that's really it's really hard to give you one. Unique, like a universal pattern to always work. But we're just going to do example for you to get some idea. Okay? You want to prove the property will actually hold on k plus 1. You can think about the plus 1 over here means we have to make some extension to the input. We assume the input is going to hold the property on size k. But now we consider a strictly larger input with k plus 1, maybe k plus 1 vertices. And we want to show that that one there also works. Extension to the input size applicable for the inductive hypothesis. And here, when you want to do the extension itself must be trying out all the possible extensions. You cannot say, I want you to choose one way to extend the graph. No, you got to choose all possible ways. That's something we'll see as well in the example we're going to do. Okay? So you can think about here also you need to consider all possible ways to extend. All right, just one more thing to say. And it must be the case that when you try to make this proof work, somehow, somewhere in your proof, the critical step is you have to apply the assumption that's made by the inductive hypothesis. Right? You have to. Has to make use of the claim assumed by the inductive hypothesis. If somehow you say that I'm able to actually prove that P holds on k plus 1 without having to use the assumption that P also holds on k, there's something wrong. Right? All right, so these are the steps you will see on every mathematical induction we're going to do. 3 steps. Okay? All right, having this in mind, let's now take a look on the property that we kind of exemplified last time. But let's now try to prove it. Okay, this one here. So what we have is the graph is simple undirected, right? So we are saying for every graph that is both simple and undirected, the following property should hold. That's what we're saying. And we're going to use mathematical induction. Okay. So what we do is we're going to prove by mathematical induction. Prove by mathematical induction. And we're going to see all the 3 steps. Okay. And you already have a decision to make, right? Obviously, you can try to make the induction on the size of V. We can make the induction on the size of E. Okay? So there's a decision to make right away. So it could be mathematical induction on the size of V. How many vertices we have, starting from maybe 0 vertices, 1 vertex, 2 vertices, and etc. Okay? Or it could be on the number of edges as well. It's also possible, right? But for this property here, Sorry, just make sure I didn't hear. Okay, yeah, okay. All right, so there is a decision to make, right? And it turns out, for this example here, we're going to choose this root over here because you can see that the summation there is trying to quantify all the vertices over the vertex set. So obviously, you can try to think about the sum. The V over here may be empty, or maybe cardinality is 1, and also cardinality is 2, and etc. I'm just looking at the property itself, because that one is really quantifying over the number of vertices. So the natural choice would be just to choose on the number of vertices. Okay? It's more like a justification. But unless the question explicitly asks you to justify why you choose to induct on vertices as opposed to edges, otherwise usually you don't need to justify this choice. Just go ahead and do it. Right? As long as you can show the proof, then it's good. All right, so this one here is nice. Okay, so we got on here, right? So there's a proof by mathematical induction. We'll go very slowly for this very first example, okay? And we'll simply opt out this option here, all right? So let's try to do base cases. We can do, well, since the question itself does not say non-empty graph, so that means we may have to consider empty graph as well, meaning that the number of vertices is simply 0, right? So step number 1. We're going to do base cases. Base cases, okay? All right, so I would say 1A. Let's say the smallest graph you could consider would be just 0, cannot be negative. When the number of vertices is simply equal to 0. That means empty graph. All right? In this case, how many edges will be there accordingly? No edge, right? Well, you can think about whenever you want to have a single edge, you need at least 2 vertices. There's simply no vertex, so there's no edge, right? All right, so accordingly, the number of edges is also equal to 0. Right? So you can think about, well, we can write it out. Sigma, and then all the V that's in empty set. There's no vertex. And then we try to do the degree of V. And it's a very obvious sigma property. If you're trying to sum up 0 terms, you simply got 0. Right? 0 is the identity of addition, right? So this will be just 0. And this will just happen to be 2 times the number of edges, which in this case is simply 0, right? So it trivially holds, but it's good to show the step. Okay. So was it good? All right, let's do another base case, right? I think it's kind of nice to really get a feel about mathematical induction. I would say the base cases are really important. Don't really think they're always trivial. It's really the insight you can really gain from the base cases that can lead you a little bit further into the more complicated case. Okay? So 1B. So let's think about if the number of vertices is equal to 1. So now, this one here is not empty graph anymore, right? Accordingly, we have to think about what are the possible range of the edges, given that there's only one vertex. Any idea? I heard 0. Okay, it's definitely possible, for example, if the graph looks like this. Now I can visualize it. If I simply got one vertex over there, let's say it's simply just called X. And it's just an isolated node without any edges. Remember, edges is simply a set, so a set can be empty, right? So that's one possibility. But we're going to think about all other possibilities, right? So now the question is, can I have the number of vertices being 0, number of vertices being 1, but I got one edge. Aha, good. The only way to have one vertex and one edge in the graph is by having a self loop. So that means the beginning and the ending vertices for the edge will be the same. Something like this. So this will make V and also E both equal to 1. However, this will violate our assumption that it is simple. So we shouldn't consider that, right? It's also important for you to know why we are not considering it, okay? So this one, no. Because self-loop. Not simple graph anymore. Okay, let me move that a little bit. I need plenty of space for later. All right, self-loop is a simple graph, right? Only one. All right, so for this one here, if you try to count, there's only one vertex over here. What's the degree for this vertex? 0, right? No edges. Very good, thank you. Yeah, that one they can repeat a sigma, okay? But that one there is going to be the degree. There's only one vertex, so we can simplify the sigma into the degree of x is simply 0, which is also equal to 2 times the number of edges, which is also 0, right? Again, it's trivial. But it's very important, I think, for 2b to really know why that number of edges equal 1 case should be excluded for a reason. All right, so we are good for base case. So for base case, let's now try to box them. And then we move on to second step. So the second step is we want to formulate or state the inductive hypothesis on certain graph, or on a graph of certain size, basically. It got to be larger than more than one vertices, more than one. Okay, I'm going to put it here. So that one there, step number 2. Okay, I'll put it here. Inductive hypothesis. Okay. So now we are going to, in this case, we are lucky because the formula itself is a property, right? We're just going to be careful about how large the vertex set is in the inductive hypothesis. Otherwise, we can just copy it. We're lucky. That's good. But sometimes it may not be exactly that. You may have to formulate the property using some sigma, using practical logic, etc. Okay. So here, we simply copy the property first. We say sigma, and then little v, member of capital V, and then we have the degree of the little v vertex should be equal to 2 times m. And not just the property, we want to say how large this assumption is, where the v, the vertex set, the cardinality should be, let's say it is equal to some number k, right? I deliberately choose k here because remember we spoke about the k right here. Right? You don't need to choose k. You can choose maybe A or B or C, X or Y, whatever. Right? But k is a very standard one. Okay? Let's say k is the scale of our assumption. And very important here to say k is larger than 1 because we are saying that it's not 0 or it's not 1. It's got to be larger than that, which is assume. K can be some arbitrary number, right? Just assume. Okay, so what you really want to pay attention to is really this k larger than 1 assumption here. Okay? And this one here is the inductive hypothesis right here. Oh, I can do better. And you can expect that later, at some point, we're going to use this inductive hypothesis. But just remember, the only place you can the only place you can somehow substitute or replace some claim by inductive hypothesis is when you know you got exactly k vertices. All right, just remember that. We'll see exactly. All right, so let's now do step number 3. Okay, step number 3 is we somehow want to show the property will actually hold on some extended input plus 1. Since we are talking about the induction on the number of vertices, we already assume k. Now we're going to add one vertex to a graph with k vertices. So now for the third part here, we are not able to draw any concrete graph because k here can be arbitrary. So all we can do is try to abstract a little bit about how the graph should look like. That's something we can walk together. Okay? So step number 3. Okay, step number 3. We have to show the property holds. Oh, you know what? Sorry, let me rephrase it. I beg your pardon. Let me start a little bit better. Okay. What we want to do is we want to make a strictly larger graph and then show the property holds. Construct a strictly larger graph with k plus 1 vertices. Okay, and then we're going to say by adding a new vertex y. Okay, it's just a very simple sentence to say that's what we intend to do. Okay, and then we'll visualize it. Just give me one moment. So this is a very important line to start with. Construct a strictly larger graph with k plus 1 vertices. Okay, and the vertex we want to add into the graph is called y, assuming that y does not exist in the old graph, right? So now let's visualize what's happening here. Okay. Think about it in this way. Let's say this cloud over here is a graph. And this graph here satisfies certain property. First of all, the number of vertices would just be k. Okay? And you can think about the k here really correspond to the k that we make its assumption in the inductive hypothesis. We know the number of vertices is k. And the number of edges is n. Also, the number of edges is also n. So we kind of know the size of the graph. We know the measure, but I don't know exactly how they look like. But it's not important. We just know that there are k vertices. If you want to somehow choose maybe an arbitrary number of k vertices, the maximum number you can choose would be just k. Okay? And then, most importantly, don't forget our friend here, inductive hypothesis. That one holds for this graph here. Okay? So from there, we say that also the inductive hypothesis holds exactly for this graph before the extension. Okay? Let me write it down again. So that means sigma v, capital V, the degree of V is exactly equal to 2 times n. All right? So this is what we know about a cloud. Okay? And the extension we want to make is by having some vertex y that's outside this cloud. Okay? So let me draw that cloud. Let's draw that vertex and put it here. Imagine that this is some vertex y. So apparently, if now we actually want to make the number of vertices exactly k plus 1, so this will be a new graph, right? We want to think about how many ways are there to really finish the extension, right? So for example, it could be that y just stands by itself. Nothing to do with the old cloud. That's one way. Or it could be that I choose maybe one vertex over here and try to connect these two vertices. Or it could be that I choose 2 vertices from here and then try to connect these two vertices to y. I can choose as many as I like, up to and including k vertices. Guys, you kind of follow? Let me repeat again. This is a very critical step. We are saying that we now want to consider a graph with exactly k plus 1 vertices. All the vertices over here we know is k. And then with plus 1, just this y vertex. And once we fix the number of vertices, let's worry about edges. How do we construct the edges? Number one, it could be that zero edge is going to be added. Y simply stand by itself, isolated. Or it could be that we can choose up to k vertices from this cloud over here, and then from there we try to connect to y somehow. All right? But how do we actually formulate it, right? That's a tricky bit. Okay? So one way to say it is like this. So let's say we somehow choose vertices. Okay? Somehow we choose vertices and then we try to connect them to y. Okay? So all these vertices chosen from the cloud, they will be connected to y. Okay? However, we have to now know very well about how many can we choose actually. Okay, so now think about here. Let me just use maybe, okay, that's good. Okay, just about here. So I'm going to write it down here so you can see that right away, but I'm going to repeat somewhere else. Okay, so we basically choose, let's say D, vertices to connect to y. And very important, the D here, what's the property we know about D? Go ahead.
Between
0 and k, exactly, less than or equal to k. So I think that's enough, right? Of course, it should be larger than, it cannot be negative, right? All right, so here, D here should be less than or equal to k. All right. Okay, let's write it down, and we'll see. Okay, so this one you can think about is more like a sketch, you know, to let you see the visual. But let's now write it down as part of the proof. So what we do is we want to choose the existing vertices and connect them to the new vertex y. And of course, so important to still remember, D here should be less than or equal to k. Think about these two lines are just about how the strategy of extending the graph. So once we can now see the extended graph, we can now try to play with the property again to see the property still holds for just one more vertex. Let's put something aside. I think that can help you a little bit. Okay. So let's think about here. Okay, I'll put it. I really want to reserve this space for some equation manipulation here. Let's keep that space clean. I'm going to write it here. Okay, I'm going to draw a table quickly. Okay. What I will do is I'm going to draw a table. I'm going to do before extension and after extension. Before and after. Okay, so what I will do is, let's do this table here very quickly, and then I would suggest we take a short break. And then, for those of you who might just want to work out the math yourself, you can feel free, or we just want to take a break, and then we finish the rest. We're almost done for this example here. Okay, but let's do the table quickly. So here, the table looks before extension. Before the extension, and also after the extension. In the actual proof, you don't necessarily have to include this table. It's more like a, just an aside for you to somehow see the various concept, okay? Before extension and after extension. Of course, the extension is about adding this y and up to d and also d edges. All right, so let's now try to figure out the value for v and e. So before the extension, we know that we got v over here, which is exactly equal to k, right? Really just here. And also e will be just m. Okay? Okay, before extension. And now, question. What about after extension? What will be the number of edges? Not what the number of vertices, first of all. Huh? K plus 1? Yeah, obviously, right? Okay, that was not bad. You can say v plus 1. Or you can say it's also k plus 1. Either way. And the plus 1 here is really the y that we have added, right? How about the number of edges? Does it change? It does, right? Should it be d or 2d? 2d? Okay. Anybody? Let me say it again. We're basically trying to say we are only counting edges now. Remember, counting edges is different from counting degrees. They are different, right? Did you want to change your answer? You want to, right? Okay, what exactly is that? Only d, right? Okay, obviously, right? If you look at the diagram here, how many edges we have added? Only this part here, just d, right? All right, so that one there is going to be the number of edges plus d, which will be m plus d. Okay, these two numbers will be something important for you to identify when we try to somehow rewrite the property slightly for this extended graph. That's what we will do. All right. Only about 1 minute or two before this one example is done. Why don't we take a short break? So for those of you who want to just see what we have done so far, you can do that. You do need a break. Otherwise, I can just take a break. Okay. Why don't we pause here? Okay. All right. So your fellow student just asked me before the break, just about right here, why it is plus d over here, right? Very good. Okay. Let's take a look again. I think it's a good recap just before we get to the final equation. So think about this is our inductive hypothesis. We say that we assume the inductive hypothesis will hold on number of vertices being k. And also we got m edges. And we also know the property holds. So now we want to make one little extension that's strictly larger than this particular graph. Okay? So the one extension we are making is we're having one vertex. Because we are doing induction on the number of vertices, just plus 1 is the most sensible option, right? That's the minimum possible extension you can make. Okay. So now, if we do have y over here, so now y, there are different ways you can connect to y. You can say there's nothing from here that will connect to y. That's one way. Or it could be that you choose one vertex from here that's going to be connected to y. Or it could be that you choose two vertices and connect to y. How many can you choose? Maximum. Oh, not infinite. How large is the cloud? K. Let's say, for example, if k happens to be 10, that means you can choose all the 10 vertices and connect all of them to y. If k is 100, you can choose 100. So you can choose up to and including k. And we just call this number d. Exactly. Good. That's very, very important. Okay. Okay, good. All right, so let's now try to see the property if that will hold on this k plus 1 strictly logic graph. So what we do is, let's start with the property. We want to do sigma right here. And then the little v is going to be quantified over capital V for sure. Can think about the capital V is the cloud. But now we got to include y. Right? So we can say union a singleton set containing just y. Are we okay with this? Right, that's very important. So now we're saying that the property is going to hold not just within the cloud, but also extend it beyond, to just have without one extra vertex. All right, and then we're going to say the degree. The degree of little v. All right, let's now do a little bit, it's not really trick, right? For sigma, basically you can think about sigma as just a series of plus. So why don't we try to say, we somehow figure out the degree sum just for this part over here. And then the extra degrees that we have to count because of y, we count it separately. So we can separate into two parts, right? Separation of concern, okay? So all we do is, you can think about will be equal to sigma over here, v quantify over only just v, capital V. And then degree of little v, think about one term. And then plus something. You can think about this part over here is going to be the extra degree counts because of y. Due to, okay, we'll worry about them one by one. What is this? Anybody? Do we know it? 2m, I like the answer, but how do you know it's 2m? Because of induction hypothesis. Because this part over here, where the universe of disclosure you can think about in some way, right? Capital V is exactly the extent right here for inductive hypothesis. So we can use 2m. Okay? And it is also important for us to know this V here. The size of V is simply K. All right? So this part over here will be 2m. By inductive hypothesis. Remember what I said earlier? It would be weird, it would be totally mistaken if somehow you can complete a proof without having to use inductive hypothesis. You have to use it, okay? All right, so this part here we know is 2m. And now the question is, what would be the additional degree counts because of y? Given that we got exactly d edges connecting between all the d vertices chosen from k vertices, and also this new vertex y. What will be the extra degree counts? I'll pause here. That's the most important part. If you got that part wrong, the math is not going to work. Let me say it again, okay? So now we want to figure out this part here, the degree counts. We know that it's simply just 2 times n. We know pretty well. But having introduced this new vertex y, and also having introduced these d edges connecting d vertices, what will be the extra degree counts? 天天? 2d, not just d. Are you sure? 2d, right? 2d as well? Okay, why 2d, right? You can think about for each of the d vertices over here, they have to count these edges. That will be d. Symmetrically, for the degree of y here is also connected back to these vertices, also another d. So degree counts is different from number of edges, right? And I think there's some little mistake you made before the break, but that's okay, right? All right, awesome. All right, let's write it down, okay? This example here, let me finish that, and I'll give you guys some intuition, like a recap, and then we'll continue, okay? Plus d, and then plus d, okay? You can think about this part here will be the degrees count from all the d vertices to y. And this d here is symmetric. It will be the degree counts from Y to all the D vertices. Bidirectional. Okay, almost there, but I want to really make sure we can end up in that good conclusion, right? I just run out of space, okay? Let's say I put a star here, okay? We're gonna continue, okay? I'll put it here, star, okay, right here. So this whole thing here is going to be 2 times n, inductive hypothesis, plus 2 times d, d plus d. Let's do some simple refactoring. 2 times n plus d. Are we done? Don't you think? What's n plus d? The new number of edges after the extension. Exactly 2 times. All right? Okay, so this one here. So this will be the number of edges after the extension. Okay, we're done. That's it. This example here, I don't think it's really trivial. You know, the concept there is very simple, right? Just a little extension here. But that one does really exemplify something we'll see a lot. Whenever you want to do mathematical induction, make sure the inductive hypothesis you really stated correctly and know the scale of the inductive hypothesis. And then when you try to introduce the extension, it's always going to help, especially for trees and graph, to really visualize how that extended tree or extended graph look like. And from there, you're going to rewrite a property. That's what you will see. You know, for Dijkstra or for minimum spanning tree algorithm, that's what we'll see as well. Okay. Guys, any question? Okay, we spent about more than 50 minutes on this example, but I think it's worth it because the mathematical induction and also get to the thinking process is so important. So definitely got to spend time. But we're going to do more. Okay. All right, please think about it. If you got any question, you can also ask me during office hour if you wish. And the property that we spoke about right in the beginning over here, this one, you can already try to see if you can apply mathematical induction to prove it. Okay, very easy. It does still involve a little bit sigma, nothing complicated, right? Exercise for you. We got about 25 minutes. Let's do a little bit concept. Well, we got more definitions. I think we're going to cover a little bit more definition also today and also Thursday. I think maybe towards the end of a Thursday, we can start a little bit about graph traversal. So we're going to dive into depth first search. We'll do depth first search first. And then we're going to do lots of tracing together. Okay, I'll let you guys know. You really bring your paper, bring your iPad, you know, be prepared to draw. And then once we finish covering the depth first search for a bit, we should really talk about how you can implement a graph so that you will get ready for assignment number 2. Not the one I'm going to release tomorrow, but it's going to be fun. Okay. Awesome. So we're going to start from the slides right here. 16, okay? Let's talk about path and cycles, okay? Actually, these two the definition are important because later on the algorithm, many of them are just about how you can find the shortest path. So you really got to know what a path is. And also you want to see, given the graph, is there a cycle somewhere? If there's a cycle, return it. Okay, so let's get the definition straight. Give me one moment. There we go. All right, let's start with the path. Okay, let's start with some definition, and then we'll switch to example right away. Given a graph, so here the graph can be whatever graph you like, right? So not necessarily simple, just a graph. A path, it was simply alternating vertices and edges. All right, so let's see some example here. So let's start with the path. Path. Okay, we're going to use this graph as an example. So it's going to be alternating vertices and edges. All right, let's see one example right away. Let me write it down first, and then we'll try to make it more visual on the graph. Okay, alternating. So let's say I start with F, and then S, and then D, and then T, and then E, and then P, and then F, and then N, and then B. In this particular example, since we actually give the labels of each edge, so that's why we can include their name over here. But in some cases, for example, when we talk about Dijkstra's algorithm, we have to think about path as well. In that case, the edge over here is not labeled with the name. In that case, we can omit the name. But for now, just learn the proper definition, right? Should be alternating the vertices and edges. And as you can see, the number of vertices and number of edges in the path should be different, right? Number of edges should be exactly one less than the number of vertices, right? That's something also obvious, okay? All right, let's say this one here is interesting, okay? That's exactly how that would look like. So what we have is, so we start with F. And then we go, oh, let me just a little bit thicker. So we start with F, and then we go through S, and then we go to D. And then we go through T, and then we arrive in E. And also we go through P here. Somehow we go back to F, which is completely okay. But as soon as you see that visually, you can see we have a cycle right away, right? But we're going to define what a cycle is, okay? So after F, we also go through N here, and then we arrive in B. That's the final destination. So it's a graph. Oh, sorry, it's a path, beg your pardon. It's a path. However, let's now also talk about cycle right away, okay? What's a cycle? A cycle is basically a path. However, that path has a very specific requirements. First of all, in order to be a cycle, the beginning and also the end vertices for the path should be the same. In the middle, we may or may not have more repeating vertices. That's what the definition says. But let's see two examples. We'll get a few examples. Okay? So let's now go back here, right here. Let's take this path, for example. Okay? First of all, you can see that just look at the F over here is repeating itself. This kind of like a subpath is called a cycle. So think about just this part over here is a cycle. Notice that you cannot say this whole path is a cycle. Notice you cannot say that. You can only say that whole path contains a cycle. But it's not a cycle. In order to be a cycle, the beginning and the end vertices should be the same. All right? Okay, let's write it down. Okay. So here we have the whole path over here. All right, so this path over here contains a cycle. The path contains a cycle. And we'll see later. As soon as a path contains a cycle, that means you got repeating vertices somehow. The path is no longer simple. Okay? Basically, a path without any cycle is a simple path. Okay? Well, we'll see that. That's also definition. Okay? All right, so that's about path and about cycle. And then let me give you another example. Okay. Let me put it here. Okay. Let's say cycle. Okay, let me give you a longer one here. Let's say we got, let's say B, N, F, P, and then E, and then T, and then D. You know what I would do? Let me do a slightly compact version. Okay, I think that'll be maybe a little bit easier. Okay, let me show the compact version. Okay, let me only show you just the vertices for now. B, and then F, and then E, and then D, and then F, and then D, and then C, and then A, and then B. Okay, let me just double check. B, F, E, D, F, D, C, A, B. Okay, Of course, since we got the names for the edges, you can also put the edges in the middle. I'll let you do that, right? But it's obvious enough how the path should look like, okay? For example, you can see that between B and F, it should be P, right? I'll let you do that additional edges, okay? So now what's interesting about this cycle here? First of all, why is it a cycle? It's because the beginning and the end, the same. So that qualifies that as a cycle. However, this is so-called not a simple cycle because the cycle within it, there's another cycle. For example, you can see that here we got D here also repeating itself. Right? And also F also repeating itself. Okay, let's try to see what's going on here. Okay? So if you try to go with that, let's say we go B and then F and then E and then we go to D and then we go to F. Now we already have a cycle, right? Like a sub-cycle, basically. After the F, we go to D and then we go to C and then we go to A and then we go to B. So we got cycles within cycle. So it's not a simple cycle. Okay? Okay, so that's also worth noting down. Oh, everything's on the slides. I just want to give you an example. Okay? So this one here is not a simple cycle. Not a simple cycle. Because there is a sub-cycle. More than one, actually. You can see one will be here and another one will be here. Okay, about cycle. Okay, so now path and cycle, right, in general. And there are notions about simple path and simple cycle. Okay, let's just see example quickly. So we also got something called simple path. Basically, it's a path containing no cycle. So there's no duplicates of the vertices, because if there's any duplicate, that means it contains a cycle. Okay. All right, one quick example here. So simple cycle, it could be, simple path again, simple cycle. It could be F and then S, D and then T and then E and then O and then A. Right? You can just feel free to visualize it on the graph, right? I'm pretty sure you can do it. Okay, one more. Simple cycle. Simple cycle is kind of interesting. It's a cycle because the beginning and the ending vertices are the same. However, if you take out the beginning and end vertices, inside is a simple path. There's no sub-cycle, basically. All right? Okay, just give you one example here. So we start with, let's say, F, T, and then D, and then R, and then C, and then Q, and then A, and then O, and then E. A, and then O, and then E. Yeah. Oh, I beg your pardon. That should be E, not F. Sorry about that. I just looked at the wrong part of the notes. All right, it's a simple cycle because, first of all, you can see that this part over here, E repeating itself. So it's a cycle. On the other hand, if you look at the rest of the path, if you look at this part here, right here, actually, you should really start with the vertices. This part over here, this is a simple path. Okay, so these are the 4 different things you gotta make sure you understand. Okay, but I'll give you one more page to clarify. Usually, there might be a little bit more confusion about simple cycle versus cycle in general. Okay, just before that, I want to also talk about quickly here something called reachable and reachable path. Okay, So usually when you say reachable, you're really talking about two vertices for you to reference to. So you would say a vertex is reachable from another vertex if there's such a path you can go from the graph. Okay, so over here, so this is the so-called reachability problem. You're basically asking, given G and two vertices, let's say X and Y, is there a path connecting X and Y? That's a reachability problem. However, the reachability problem is very easy to be solved once we learn about how to traverse the graph. That's something we'll see. Okay? It can just be more like a byproducts by traversing the graph. Okay, that's good. And this particular graph, just a little bit look ahead, we call that this graph over here is connected because if you pick any two vertices in the graph, they're simply reachable to each other. Right? But don't worry, I'll define what a connected is, either today or Thursday or Wednesday. Okay? So you can see if you choose A and E, apparently they're connected. They're reachable to each other. If you pick maybe A and D, also they're reachable to each other. At least there's one path over here, or can be another path. As long as there's at least one path, they are reachable to each other. Okay? Okay, good. And let me clarify very quickly, just a little bit more. Okay? Okay. Just about simple cycle and not simple cycle. And you guys can read about the definition here, right? So let me just go over the example quickly. So we'll talk about simple and not simple. So we got simple and also not simple, okay, cycle. You got to look at the middle part, actually, for the cycle itself. If the middle part is actually a simple path, then it's a simple cycle, okay? Okay, so this one here is just another example. But you can see in both cases, the beginning and also the end. And also the beginning and also the end, they are the same. So both are cycles. It's just a matter of being simple or not simple. Okay, so here I got A connect to, oh actually, what? I think this one's good enough. You can see just the middle part over here. This part over here is a simple path. So that means this entire cycle over here is a simple cycle. On the other hand, if now you look at the middle part over here, is this a simple path? Not really, because there's a cycle in the path, right? Because that one there, you can see the B and B here, they are not simple path. Not simple path. So that means the whole thing over here is not a simple cycle. Good? Okay. Okay, we got about 8 minutes. I think I can cover some. But in the following list of definition, you can start to create some confusion about exactly what should be what, right? So I would suggest for those of you who actually like to take notes or to create some flashcard for yourself, it might be a time just for these terms. There are so many terms you have to somehow distinguish, okay? So let me just enumerate just some of them just to see. Okay, we'll cover as much as we can today, but we'll continue on Wednesday, okay? We're going to start by talking about what a subgraph is. And then we're going to talk about what a spanning subgraph is. And then we're going to talk about what a connected subgraph is. Okay, and then after that, we're going to talk about what a forest is. Forest. And then after a forest, let's talk about what a tree is. And then after that, we're going to talk about what a spanning tree is. These are just examples, right? There'll be more. And of course, given that there will be no data sheets for the exam and the test, you want to really get these clarified, right? I'll help you, don't worry. I do have a table to kind of compare for you, okay? Okay, let's now go over some of them, and we'll definitely do the rest on Wednesday. 5 minutes, five or six. Okay, subgraph, let's do that. So for subgraph, we can easily use some mathematical equality or set relationship to express. Okay, there's a path and cycle. You'll just see more example on the slides. Okay, subgraph. Okay, let's see. Okay, right here. Yeah, I think this will be good enough just for the rest of today. Okay, let's say we are given this particular graph, right? We know that for every graph, you can simply formulate it using a tuple, a pair. The graph will be V and also E. And as you can see, the V will be 1, 2, 3, 4, 5, 6. And the E here will be 1, 2, 3, 4, 5, 6, 7, 8. Right? So these are the 8. And what's the definition for a subgraph? Very simple definition. Given that V and E are simply set, as long as you can create another graph for me that's simply just going to be a subset of the V or E, is a subgraph. Very generous definition. Okay, I'll show you an example. First of all, if I got a subgraph, let's call that G prime. And the G prime here has V prime and also E prime. So what would be the conditions for the G prime to be a subgraph of G? So now we are really trying to draw a relation between V and V prime and also E and E prime, right? Basically, such that V prime a subset of V. Also E prime a subset of E. All right, so that's the definition. And let's try to somehow enumerate some examples systematically. All right. Well, usually once you give some property, you may want to think about what's the minimum subgraph and what's the maximum subgraph. Why don't we start with that? According to this definition here, what would be the minimum subgraph of this particular subgraph over here? Minimum. Empty graph, when the V and E happen to be empty. Absolutely. Okay. So subgraph number 1. Put it here. Number 1. So it could be that G prime. Okay, let me just say G1. Okay. G1 will be just empty graph, where empty will be a subset of any V. And also empty edges will be the subset of any E as well. So this will be the minimum possible subgraph. Okay, that's a minimum. Let's go the other extreme. What will be the maximum subgraph? The G itself. Because you cannot go beyond V and E, right? Got to be exactly the same, right? That's really the maximum possible. All right, very good. Okay, number 2, G2. Okay, so let's say will be exactly V and E. Let's say this, V prime and E prime, such that B prime will just be V, and also E prime is simply equal to E, right? So that's still a subset for sure. We're still satisfying the definition for being a subgraph, okay? So this will be the maximum subgraph. Maximum subgraph. All right, and then let's now just look at some other example, right? Let's say this one here. G3. Let's say I just want a one vertex graph. How about G3 is simply like that. It contains just the E vertex and then no edges. Is it a subgraph? It is, right? You can think about G3 here is basically like this. I'm basically just covering just this vertex over here. So the subgraph is just by itself, without any edges, which is okay, right? Apparently, oh, sorry. So here you can see the E here is a subset of the original V, and also empty is also a subset of E, all right? Now, question for you. How about this? G4. Is G4 a subgraph? Well, I agree. In some way, if you check the condition, empty set is a subset of V, yes. And also R is also a subset of the edges as well. However, this is not even a graph. That's a problem. You cannot have a graph just by the edge itself, right? So these conditions, yes, but also it should be a graph itself, right? G4 over here, this is not even a graph. Give me 1 minute and then we're done. Not even a graph, because if you simply got one edge over here, R, without beginning and also ending vertices, it simply doesn't make sense, right? So G4 here is not even a subgraph, all right? All right, so I think the most important thing for you guys to really revisit is the mathematical induction we did. And then I'm going to release your assignment number 1 definitely tomorrow, but I'm just not exactly sure how early or how late. But for sure, you will see that tomorrow. And then get started, and we'll talk about it on Thursday tutorial. Thank you.